general relativity step by step. I'm going to set up a coordinate system, and I'm going to set up the simplest possible vector field on it. Constant vector field. Constant. All in the same direction. So this would correspond, I guess, to the velocity vector of little creatures crawling along. Constant. And I'm going to write it down in a slightly peculiar way, of course. I'm going to write V equals alpha EX plus beta EY, where EX and EY are my basis vectors in a Cartesian coordinate system. And it's absolutely constant. And if I want to work out what the rate of change of this is, if I go V, let's say, so hang on a minute. So V1 equals alpha and V2 equals beta, constants. They don't change. So if I work out di V1 by, no, not by alpha, by x, di V1 by dy equals 0, super. Constant. Di V2 by di x equals di V2 by dy equals 0, because it's constant. Everything works nicely in a Cartesian coordinate system. What I'm going to do now is think about what happens in my strange h theta space. There's h, there's theta, x equals h, y equals h tan theta. What happens to my vector v when I express it in terms, or v bar I guess, I equals v bar 1 eh plus v bar 2 e theta. What happens if I have di v bar 1 by di x1 equals di v bar 1 by di h equals what? Well, this is quite an interesting thing. Let me just remind myself what my basis vectors are. Eh equals di p by di h. So what happens to my point there when I change h but I don't allow theta to change? It goes up there. That's going to be ex plus however far you've gone upwards, ey tan theta, which I've done zillions of times. And e theta equals ey times h sec squared theta, which again I've done zillions of times. So I'm not going to do that again. So what I want to work out is to work out what the barred components of this vector are. V in the barred coordinate system, v bar 1 e h plus v bar 2 e theta. Now to work out this I could use the tensor transformation law, which is v bar I equals what? Di x vj. That's unbarred and the j is upstairs, so it's got to sum with a j downstairs. Unbarred with unbarred. That's barred, so that's barred there. And that's the contravariant tensor transformation law. Now I could use that to find these guys, but I'm going to use a slightly different method just to make it a little bit more transparent, I guess. So let me just say that v, my vector, is the same vector here all the time. It's this constant vector here, which is this one here. I want to work out what that is in the barred coordinate system. I want to work out what it is in the barred coordinate system. I want to work out what that is, and I want to work out what that is as well. Well, let's just have a think about that. Let's call it alpha bar e h plus beta bar e theta. And that is, as a whole, equal to alpha ex plus beta ey. As I say, I could use this formula here for the tensor transformation law, because I've established that it's a tensor, and I'm not going to. I'm going to use this, because it's easier. So alpha bar, and what was EH? EH was this, EX plus EY tan theta, plus beta bar times E theta, which from this formula here is H sec squared theta, EY. And that equals my original vector, which is alpha EX plus beta EY. And of course, EX and EY behave themselves. They're nice, friendly things. So I know that alpha, actually, why don't I do it formally? I'll take a dot product with, what I was going to do is just balance the terms, but I'll do a formal derivation with the EX, because I know that EX dot EY equals 0, because they're at right angles. So when I take a dot product with EX, everything vanishes except for the EX terms, and I've got alpha bar EX dot, of course, EX dot EX equals 1, of course. So when I take a dot product, I've got alpha bar, this term drops out, equals alpha. Oh, that's easy. Now I'll take a dot product with EY, of course. Dot with EY. Write that out a bit more neatly. EY. And what do I get? I get alpha bar times tan theta plus beta bar times h sec squared theta equals beta. But I know that alpha bar equals alpha. So I've got alpha, so I've got beta bar equals h sec squared theta equals beta minus, take this over to the other side, substitute for alpha tan theta. So I've got beta bar equals beta minus alpha tan theta over h sec squared theta. Emphatically, and I've got alpha bar equals alpha. So that one's a constant. This is definitely not constant. So what that tells me is, even though I've got a constant vector field, there it is, very constant, can't get much more constant than that, when I express it in Cartesian coordinates, everything's hunky-dory, everything's nice and sweet, and all the derivatives, it's all wonderful stuff. However, we've got this rather awkward fact that di V1 by di H equals di V1 by di theta equals 0, no problem. But di V2 by di H is equal to this thing here. Oh no, have I got it the wrong way around? No, I haven't. The alpha is constant. The alpha is constant. But di V2 di H is di beta bar by di H equals the differential with respect to H of this thing here, minus alpha tan theta over H sec squared theta. It's a mess. Not constant. We've also, of course, got di beta bar by di theta, which is di by di theta of beta minus alpha tan theta over H sec squared theta. Absolutely not constant. Or actually, it's the different. This thing in here is not constant, but the differential is non-zero, and that's non-zero. So it's not constant. So the differential of a non-constant term is not equal to 0. So what that tells me is that V bar I by di x bar j is not necessarily equal to 0. Which is kind of obvious, really, because the basis vectors are changing. The basis vectors themselves, there they are moving about. So the differential of something constant with respect to something that's changing is going to be non-zero. So yeah. So this is a bit of a problem, because calculus is quite a useful tool. Calculus is cool. Calculus is nice to have. And when we're considering general curvilinear coordinates, it would be nice if the derivative of a constant vector field was equal to 0. And that's not the case. So we're going to have to think carefully about what we mean by differentiation. We're going to have to think carefully about what we mean by constant. We're going to have to think carefully about lots of things. And this is on a flat space. This is on a flat two-dimensional plane. So if our ideas don't work very well on a flat two-dimensional plane, we haven't got a Welch chance in a supernova of making it work in some complicated four-dimensional Minkowski or curved Minkowski space. So we're going to have to get this right. And once we've got it right, we'll see how to apply it to relativity. And I'm going to stop there. It's been too long already. 10 minutes this one. too long.